Consider a mechanical wave equation like this. Y is equal to a sine kx minus omega t plus phi. Okay. Now, wave, as you all know, is basically a disturbance in some property which propagates from one place to another. In a mechanical wave, what we disturb is the mean position of the particles, okay, of a particular medium. Mechanical waves require a medium for propagation. So disturb one particle of the medium, that particle will disturb the next one, that next particle will disturb the particle after it, and so on. The disturbance propagates along the medium. That is what is a mechanical wave. So if you have a wave equation like this, can one of you tell me what Y stands for? Suppose this represents a transverse wave. Okay, what does Y mean?
Sir, is it displacement of particle?
Displacement of the particle from mean position, correct. Okay, so basically it's the disturbance that we produce in a particular particle. Okay. Displacement from mean position. Good. What does A mean?
Amplitude.
Amplitude. That's nothing but the maximum displacement of a particle from its mean position, either way, either in the positive direction or in the negative direction. So A is amplitude. That's the maximum extent to which it can get displaced from mean position in any one direction. Okay. What is K called? Okay, K is called propagation constant of that wave. Okay. And omega, as we know, it is called angular frequency of the wave. And finally, phase constant phi. Okay. Phi is called the phase constant. Or you can also say the initial phase. You put x is, see what is phase? This entire bracket, okay, the complete sign bracket is called phase of the wave. Fine. In that phase expression, if you substitute x as 0 and t as 0, the phase will be phi. Okay. So phi can also be called as the initial phase of the particle at x is equal to 0. Anugrah is asking, isn't k angular wave number? You can call it angular wave number, yes. Okay, but it's called propagation constant. Yes, it is related to wave number. You can call it angular wave number. Fine. So Y basically tells you to what extent a particular particle is disturbed at a particular instant. Okay. For example, just a moment. I'll take one wave diagram. So imagine there's a transverse wave like this propagating along the x-axis. At a particular instant, as the wave is propagating along the x-axis, at a particular instant, let's say you take a photograph of the string. Okay, assume it's a wave on a string. You take a photograph of it, it looks like this. Okay. Now, let's assume this is the origin. So for a particle at a particular x coordinate, let's say this one. Okay. At this time, at t equal to 0, that particle has gone here. Okay. That particle of the string has been displaced in the positive direction. Okay. So some particles have positive displacement. Another particle, if you consider some other random x coordinate, maybe this one. Okay, at this x coordinate, whatever particle was supposed to lie on that string, okay, lie on that horizontal line, has gone down, has been displaced in the downward direction. Fine. So that is what the wave equation tells you. It tells you the y coordinate. Okay, this is the y coordinate of this particle there. This will be the y coordinate of this particle, some positive, some negative. So at any instant, at any x coordinate, how much is the disturbance created is what the wave equation tells you. So it has to depend on position as well as time. Okay. And as the disturbance propagates forward at different x coordinates, or I should say at a fixed x coordinate, okay, at different times. Yeah, we'll discuss that for a fixed x coordinate at different times, you'll have different displacements. Obviously, this is a sinusoidal wave. So the particle at a particular x coordinate will keep oscillating up and down. Okay, they will execute simple harmonic motion. Fine. This particle oscillates up and down. That's what happens in a transverse wave. This particle also oscillates up and down. So for a fixed x coordinate at different times, the particle will have different y coordinates. Sometimes it will be at the positive extreme, sometimes it will be at the mean position, sometimes at the negative extreme. Okay, it keeps oscillating up and down. That happens at every x coordinate. Okay, so at a fixed x coordinate, time to time, the disturbance should vary. And at a fixed time, position to position also, this disturbance should vary. Obviously, see, we have taken a photograph here of the string. So here it means time is fixed. At particular instant, this is the shape of the string. Now you can see here that different particles have been displaced to different extents. Some of them are at their positive extreme, some are at their negative extreme, some particles are at their mean positions. Okay, some are in the process of moving up, some are in the process of moving down. Fine. So that's what wave equation effectively tells you. And what about the phase constant? The phase constant, you substitute x as 0 and t as 0. x0, t0. Using the phase constant, you can tell what is the y coordinate of that particle, x equal to 0 at t equal to 0. Not just that particle, you can tell the y coordinate of any particle at a particular time using that phase constant. Okay, at the initial time using that phase constant. Okay, so this is the general equation of a sinusoidal mechanical wave, where the wave is propagating along x-axis and disturbance is in the y direction. Okay, now we are talking about electromagnetic waves. As the name suggests, these are waves of electric field and magnetic field. Okay, now Faraday proved that, or Faraday discovered that a time varying magnetic field produces an electric field. And Maxwell discovered that a time varying electric field produces a magnetic field. That is how an electromagnetic wave propagates. Somewhere in space, let's say a time varying electric field is created. Automatically that will create a time varying magnetic field, and that time varying magnetic field will create another electric field. That electric field will create another magnetic field. That is how an EM wave propagates. Okay, so like see, in this mechanical wave equation, we are writing the equation of displacement of a particle from its mean position, because in a mechanical wave, that is what happens. We literally disturb the particles of the medium. In an electromagnetic wave, what effectively happens is electric field and magnetic field get produced at different points in space. Okay, I should not even use the word medium, because electromagnetic waves can propagate in vacuum also, and also in any medium. In any medium they can propagate. So in an EM wave, effectively what happens at a particular point, if you consider at a particular x coordinate, let's say x naught, at one instant, some electric field will get generated. At another instant, some other electric field will get generated. Okay, the electric field will become stronger, weaker, then it will even change direction, become stronger in the opposite direction, and again weaker in that direction, and so on. So the strength of the electric field at a particular point keeps changing. Similarly, the strength of the magnetic field at a particular point also keeps changing from time to time. And at a fixed time, at different points, there will be different electric fields produced and there will be different magnetic fields produced. Okay, so an EM wave equation will look very similar to the mechanical wave equation of a transverse wave. Okay, can one of you tell me how electromagnetic waves are generated? What produces or releases electromagnetic waves?
Time varying electric field and magnetic field.
Okay, but how does that get produced? There's a time varying electric field, there's a time varying magnetic field also. What produces those?
EMF.
No. You are telling the theoretical answers, like how to produce EM wave or what happens in an EM wave, but practically how do they get generated? Okay, electromagnetic waves are produced by accelerated charges. Okay, charges moving at constant velocity cannot produce. Charges at rest also do not produce electromagnetic waves. But if there's an accelerated charge, then they give out electromagnetic waves. Means they lose energy by radiating electromagnetic waves. Wave is nothing but transfer of energy and momentum. If something is producing waves, means it is giving out energy. So accelerated charges produce electromagnetic waves. Remember this point. How exactly and all is not necessary for you at this point, but they are produced by accelerated charges. And as they produce electromagnetic waves, they are giving out energy. So accelerated charges will keep losing energy, okay, by producing electromagnetic waves. And next property, as we say, electromagnetic wave, we know that there will be an time varying electric field and simultaneously there will be a time varying magnetic field also. Okay, it has been found that the electric field and magnetic field, okay, in an EM wave are mutually perpendicular always. Okay, what do we mean by this? At a particular point in space, suppose an electromagnetic wave is traveling, means a disturbance in electric and magnetic field is traveling. Okay, the electric field produced at that point in space and the magnetic field produced at that point in space itself, they are mutually perpendicular to each other. Okay, it has been found experimentally. Angle will always be 90 degrees between them. And the electric and magnetic fields are both perpendicular to the direction of motion of the wave or direction of propagation of the wave. Okay, therefore, in an EM wave, we can say the electric field, magnetic field, and the velocity of the wave are mutually perpendicular. Okay, these are some properties of electromagnetic waves. You just need to remember these, fine, and apply them in problems. Next, now they are mutually perpendicular, that's fine. So if one is in the X direction, one is in Y direction, the third one will be in the Z direction. Or you can say, suppose velocity is in the X direction, then electric and magnetic fields will be in the YZ plane. Okay, perpendicular to each other, they can be anywhere in the YZ plane. Like one may be making 45 degrees with the Y axis, positive Y, positive Z. The other can be making 45 degrees with positive Y and negative Z. They should be perpendicular to each other, that's all. So they could be anywhere in the YZ plane perpendicular to each other. Okay. And it has also been found that the relation between their directions is velocity is always along the cross product of E cross B. Okay, it's not the other way around. You know that if you reverse the order of vectors in cross product, the direction of the cross product changes. Okay, so the direction of propagation of an EM wave is always along the direction indicated by E cross B, electric field cross magnetic field. Okay, Let's discuss one small problem based on this. Suppose electric field is towards north. Okay, electric field in an electromagnetic wave is towards north, and the magnetic field is towards west. Okay, north and west are perpendicular to each other, so that's fine. If electric field is towards north and magnetic field is towards west, what is the direction of propagation of the EM wave? Type your answers in chat. You just have to visualize the cross product properly. Okay. Anugraha, give answer in terms of the usual everyday directions, like north, west are natural directions, no? So your answer also should be in terms of something like that. And I got one answer as south. It cannot be south. Okay. If one of the vectors is along north, then the cross product cannot be in the south direction. Okay. See, north, east, west, south are, as I said, natural directions. Suppose north is in front of you. Okay. You are facing north. Then which way will west be? West will be to your left. Then you have to take E cross B. So north cross west. Okay. So place your right hand fingers due north. I'm assuming forward is north. My left is west. This is left for me. So I'll curl my fingers to the left. Okay. So electric field cross magnetic field, north cross west. Thumb is pointing in the upward direction. The answer is upward, vertically upward, towards the sky. Okay. So electromagnetic wave is going in the upward direction. This particular wave. Is this clear to all of you? Any doubt in this? Rishi, did you understand?
Yes, sir.
Okay. Radyun, what about you? Okay, fine. So remember, the electric field, magnetic field, and the direction of propagation of an EM wave are always mutually perpendicular, and the direction of propagation is along E cross B. Okay. Next, see, we know in an electromagnetic wave, there is a time varying electric field, and along with it, there is a time varying magnetic field. Okay. These two, the electric field and magnetic field, vary sinusoidally with time. Okay. That means the electric field will be a sine function of time. Sine or cosine, both are called sinusoidal. Okay. Sine can be converted to cos, cos can be converted to sine. They're not really different functions. So electric field varies sinusoidally with time. Magnetic field also varies sinusoidally with time in an electromagnetic wave. See, if they're varying sinusoidally, that means they increase, decrease, they become negative, increase, again they decrease, come back to zero. They'll keep oscillating. They're oscillating functions basically. Okay. And it is found that the electric field and magnetic field at a particular point We already discussed that they are perpendicular to each other. The electric and magnetic field at a particular point oscillate in phase with each other. What does this mean? Okay. See, consider something like this. At a particular position, an electric field and a magnetic field have been set up. Okay. Assume there's an electromagnetic wave propagating along that gray line, along the x-axis. Okay. Now, wait, E cross B should be in the direction of propagation of the wave. I took electric field in the y direction, magnetic field is in the z direction. I could have taken it whichever way I want. Just a moment. I'll write B on this side. So when electric field is in the positive y direction, magnetic field is in the positive z direction. And if you take y cross z, you will get x, positive x. Okay. So basically what happens at a particular point, okay, let's consider the point on the right side. Okay, this one, let's say it has an x coordinate x1. At that x coordinate at a particular moment, these are the electric and magnetic fields that have been set up. Electric field, some electric field has been established in the positive y direction. Some magnetic field has been established in the positive z direction. Okay, and this has been created by the electromagnetic wave propagating through that point. Fine. So when the electric field has a particular strength, magnetic field will also have a particular strength. Now we know that in an electromagnetic wave, there's a time varying electric field. So at this point itself, next instant or a short while later, a slightly stronger electric field could get produced. In the same direction, a slightly stronger electric field. Then automatically a slightly stronger magnetic field also will get produced. As the electric field strength increases, the magnetic field strength also increases at that point. Okay. When the electric field reaches its extreme value, peak value, okay, see, it's an oscillating electric field. It will rise to an extreme and then decrease again. Okay, so when electric field reaches its peak value, at the same instant, the magnetic field will also reach its peak value. After that, the electric field strength decreases. Simultaneously, the magnetic field strength also decreases. That is what we mean by the two fields being in phase with each other. As one increases, the other decreases. When one reaches the peak value, the other also reaches the peak value at the same time. As one decreases, the other also decreases. Okay, and after some time, they'll become negative. You will see electric field getting produced in the negative x direction. Then at that instant or at that time, the magnetic field will get produced in the negative z direction, like this. And in the negative x direction, as the field becomes stronger, electric field becomes stronger, the magnetic field also becomes stronger. And again, in the negative direction also, they will reach their peak values at the same time. So when the electric field is at its negative extreme, the magnetic field will also be at its negative extreme at the same instant. Okay. Again, they'll decrease, they'll increase on the positive side, they'll decrease, they'll increase on the negative side. That cycle will keep on keep on happening as long as the electromagnetic wave passes through that point. Okay. So they are both sinusoidal functions and they oscillate in phase with each other. Now see, in a mechanical wave, there's a mechanical disturbance. There's some displacement which the particle of the wave undergoes. And we represent the displacement like this. In an electromagnetic wave, the particles don't get disturbed. The particles stay where they are. Or there may not be a medium at all. There may not be any particle at all. Okay. But what happens is at a particular position, maybe an x coordinate or a y coordinate or a z coordinate, whatever it is, at a particular point in space, the electric field strength increases, decreases. Okay. So we need to write an equation for the electric field strength and the magnetic field strength. That is how we represent electromagnetic waves. Okay. So the wave equation in an EM wave equation, we must indicate how the electric field and the magnetic field vary with time and space, or with time and position, I should say. Okay, now these are sinusoidal functions. So you can simply write like this. the electric field, suppose the electric field is in the y direction, okay, like the example that I took. Then we can write electric field in the y direction is equal to a sinusoidal function, which will have a peak value. Let's say the peak value is E naught. That's the highest or the strongest electric field which the EM wave can produce at a particular point. Sine some propagation constant or angular wave number into x. Now, this x will be used here if the wave is moving in the x direction along the x-axis. Suppose wave is going in the y direction, then you'll have to put y inside that sign bracket. If wave is traveling in the z direction, you'll have to put z in that sign bracket. Okay, that adjustment you need to make. I'm assuming the wave is traveling along the x direction. Okay. So sine kx, it could be plus or minus omega t plus some phase constant. So when you write an equation like this, understand what you are representing. You are writing an equation for electric field produced in the y direction at a particular x coordinate at a particular time. Okay, so from coordinate to coordinate or from position to position, you can tell how the electric field varies using this equation. At a particular position also, time to time, you can tell how the electric field varies using this equation. So this is how we represent the electric field of an EM wave. And since it's in the y direction, you can include a j cap here. That's all. And along with this, a magnetic field also will exist. Okay. Now we assumed wave is moving in the x direction, and we assumed electric field is produced in the y direction. Then the magnetic field gets produced in the z direction. It will also have some peak value of its own. And we said these two will be in phase with each other. Means whatever is the phase of the electric field equation, same will be the phase of the magnetic field equation. So that makes it very easy for us to write the magnetic field equation. Kx plus or minus omega t plus phi naught. And this is in the z direction, so k cap. That's all. This is how we represent electromagnetic waves. We write the equations of their electric field and magnetic field as functions of position and time. Okay. Now see, if you observe the electric field and magnetic field equation, they are mostly the same except for the peak value. And it has been found that the peak values have a relation between them. The peak value of electric field is C times the peak value of magnetic field, where what is C?
Velocity of light.
Speed of light in vacuum. Actually, I should say, to be more precise, we should say speed of the electromagnetic wave. Light is an electromagnetic wave, we know that. Okay. C is when it is in vacuum. If it's traveling in some other medium, no, you have to use the speed in that medium. Okay. So it is better to write E naught is equal to V into B naught, where V is speed of the electromagnetic wave. Okay. Whatever wave you are trying to represent, its speed is V. Okay. So in vacuum, it changes to E naught is equal to C times of B naught, where C is 3 into 10 power 8, approximately 3 into 10 power 8 meters per second. Okay. Now in other media also, be it water, glass, any medium through which EM waves can travel. Okay. EM waves can travel through like opaque medium also. It can even travel through walls. They can travel through walls also. Okay. Let it be. But depending on the medium, the speed will change. But still, it will be a significantly large speed compared to the everyday speeds that we come across. Okay. So V will usually be a large number. Now, if V is a large number, then you can say that numerically, okay, forget about the units. We know they are different quantities altogether. Electric field, magnetic field are different quantities. Numerically, E naught will be very large compared to B naught. Okay, see, it's wrong to compare an electric field and a magnetic field, but when you express both of them in SI units, you will have a certain numerical value for them. Okay, that numerical value of electric field will be very large compared to magnetic field. And this is the reason when we represent electromagnetic waves Okay, we show the electric field of the wave. We don't indicate the magnetic field at all, because see, it's a basic principle in vectors that magnitude of the vector should be proportional to length of the vector. Now in an electromagnetic wave, there's an electric field and also a magnetic field. So you are supposed to show both of them. But suppose you draw electric field vector like this. Fine. Or let's say this is the peak value of electric field. The peak value of magnetic field will be very, very small. Even if you draw the vector, you are supposed to draw a very short vector like this. You can't even show it here actually. Okay. It suppose it's vacuum. The peak value of magnetic field will be 1 by 3 into 10 power 8 times the peak value of electric field. It's very, very small. Okay. I'm not saying the field is negligible. Okay. Numerical value is very small compared to numerical value of electric field. Now for electric field, a moment. Are you all able to see my screen?
Yes, sir.
So yeah, because the numerical value of electric field is so high compared to the numerical value of magnetic field, we usually indicate or we usually represent only the electric field of an EM wave while drawing. Okay. Actually, what I have drawn here is meaningless. If this is the electric field, I can't even show how small the magnetic field is in a diagram like this. Okay, but just for you to be able to understand, I have drawn it like this. Okay. So if you know the peak value of electric field, you can find out the peak value of magnetic field. They are not completely independent of each other. So if you know the electric field equation, you can on your own write the magnetic field equation. You don't need to know both the equations separately, because the phase will be same anyway. You'll take it as it is. And the peak values, you know how they are related. Then you can draw one, you can write one equation based on the other. Okay. So in an EM wave, you don't have to mention both electric and magnetic field. You mention one of them, that will be enough. Okay. And next is the speed of wave. Can one of you tell me generally on what factors does the speed of a wave depend?
Wavelength.
No. Speed of wave does not depend on wavelength. You can calculate it based on wavelength maybe. Okay. It does not depend on that. Like you all must be knowing this equation. Yeah, it depends on the medium actually. You all must be knowing this equation. V is equal to F lambda. This is a general equation for any wave, where F is the frequency, lambda is its wavelength. Okay. You can calculate it based on these, but it does not depend on these. Okay. As Anugraha mentioned, the speed of a wave, any wave, be it mechanical wave or electromagnetic wave or any other wave that you know of, okay, it depends on the medium, properties of the medium through which it is propagating. Okay. You must have studied in 11th class in chapter waves. Mechanical waves, okay, be it transverse wave or longitudinal wave, okay, waves on a string or sound waves, they depend on elastic and inertial properties of the medium. Okay, let me just remind you a little, some formulas. Velocity of a transverse wave on a string is under root T by mu, where T is tension in the string and mu is the linear mass density of the string, mass per unit length. Okay. Speed of sound in a particular medium is under root beta divided by rho, where beta is the bulk modulus of that medium, rho is the density of the medium. Okay. And in air, it becomes gamma p by rho, all those things. Like there will apply principles of, some ideas from thermodynamics and all. We treat air as an ideal gas, then we can find out the speed of sound in air also. So basically, velocity of any wave or the speed of any wave depends on properties of the medium through which it is propagating. Mechanical waves depend on elastic and inertial properties. Now see, electromagnetic wave, how quickly it propagates depends on how easy it is to set up an electric and magnetic field in that medium. Obviously, it should depend on that. And what properties of a medium tell you how easy it is to set up an electric field or a magnetic field? Permittivity and permeability. So the speed of an EM wave depends on permittivity and permeability of a medium, of the medium, I should say, in whichever medium you want to find out the speed. Fine. And the proper formula for this is speed is equal to 1 by under root mu epsilon. Permeability, permittivity, you'll have to multiply them. Okay. So in vacuum, you can say speed of light in vacuum, that is C, becomes 1 by under root mu naught epsilon naught. You can even substitute their values and check. You will see this is approximately equal to 3 into 10 power 8 meters per second. Okay. So remember, generally speed of wave depends on properties of the medium. Okay. Speed of electromagnetic wave depends on permittivity and permeability of that medium. Now, we know that relative permeability mu r is nothing but permeability of the medium divided by that of vacuum, and relative permittivity, which is nothing but dielectric constant. Okay. Relative permittivity is permittivity of the medium divided by that of free space or vacuum. Therefore, mu can be written as mu r into mu naught. Epsilon can be written as epsilon r into epsilon naught. So the speed of an electromagnetic wave generally can be expressed as 1 by under root mu epsilon, which changes to 1 by under root. Mu is mu r mu naught. Epsilon is epsilon r epsilon naught. Okay. And from this, if you remove 1 by under root mu naught epsilon naught, that becomes C. So you can write it as C divided by under root mu r epsilon r. So if you know relative permittivity and relative permeability, you can tell what is the speed of electromagnetic wave in that medium. Mostly they'll ask questions about vacuum only. In case it's some other medium, remember, if medium changes, speed changes. Okay. How is relative permeability mu r related to susceptibility? Can one of you tell? How do you express relative permeability in terms of susceptibility? Okay, this is from magnetism and matter. Mu r is equal to 1 plus x. That's all. X or chi, whatever you prefer calling it. Fine. So it all depends on what information they want to give you and how much they want to test you. They can tell you mu r values directly. They can say that the wave is propagating in vacuum, or in some other medium they can give mu r epsilon r, or they can give mu epsilon of the medium directly, or they may give you susceptibility if they want to test this also. Okay, fine. So simply based on the medium in which it is propagating, based on properties of the medium, you can tell with what speed it is traveling. Okay, and let's use this equation. Suppose the electric field of an EM wave is indicated like this. Now we know E0 is the peak value. Okay. So you can say this is the amplitude of electric field. They don't use the word peak value, they use the word amplitude of electric field. Now we know K is propagation constant or angular wave number. What can we find out based on K, or what does K depend on? What does K depend on? Okay, listen. Can one of you tell me what is the period of repetition of this function? Y is equal to sin x. What is the period? After what interval does it repeat itself?
2 pi.
2
Pi,
pi.
sir.
2 pi. Okay. After every change in 2 pi, whenever x changes by 2 pi, you see the graph repeating itself. Okay. Suppose you have y is equal to sine of 2x. What is the period of this function if you know? Anugraha, what you said is correct only. K depends
Is
on
it 4
wavelength.
pi?
It's not 4 pi. Listen, you should understand the basics. Sine function repeats itself whenever what is inside the sine bracket changes by 2 pi. So this function repeats if 2x changes by 2 pi. 2x changes by 2 pi means x should change only by pi. So the period of this function is pi itself. Okay, pi only. Just a moment, let me show you the graph, you'll understand better. Okay, this is the graph of y is equal to sine 2x. Nothing new in this, just to show you that period of repetition. Okay, let's consider one cycle of this, maybe from this point to this point. Okay, see here on the x-axis they have taken 1, 2, 3, 4 and so on. You can see that the cycle repeats itself. Like you can say this is one repeating unit of this graph. Okay, we call it as a pulse. This is one pulse. Basically, the graph is a collection of pulses like this. Now, how long is the pulse? 3.14. That is exactly pi. And it repeats itself after that interval. Okay, so the period of y is equal to sine 2x is 2 pi divided by 2, I can say. Okay, it's better to take it that way. That is pi. Similarly, y equal to sine 3x will have a period of 2 pi divided by 3. And generally, y is equal to sine kx will have a period of 2 pi by k. Kx has to change by 2 pi, means x has to change by 2 pi by k. After that, the shape will repeat itself. Okay. Now, let's consider a general sine graph. Suppose this graph's period is 2 pi by k. Okay, I'll consider one repeating unit of this, one pulse of this, maybe from here to here. Now you imagine this as a wave. Okay, as a sinusoidal wave which is propagating in the forward direction. Now this 2 pi by k is the length of this pulse. It is also the distance between two successive crests. This will also be 2 pi by k only. It is also the distance between two successive troughs. From here to here also it will be 2 pi by k itself. Because you can think of that also as a repeating unit. For example, this crest to this crest. You can say that is one pulse and it repeats. Fine. And in terms of properties of a wave, what is the distance between two successive crests called? In a wave, distance between two successive crests, what is it called?
Wavelength.
Wavelength. Okay. So this 2 pi by k is nothing but wavelength of the electromagnetic wave. So k depends on the wavelength. Fine. The propagation constant or angular wave number, you can call it whatever you like, depends on wavelength. Like based on this function, mathematically you can say, see there is a sine kx term, right? So you can say k or not k, you can say 2 pi by k is the x value after which the function repeats itself. So you can say it's the distance after which the shape repeats itself. So that automatically becomes the wavelength. Similarly, you can observe that in the wave equation itself, omega is the coefficient of t. Now, if you have a function like this, y is equal to sine omega t, here t becomes a variable, then this thing's period of repetition is 2 pi by omega. Okay, so you can say omega is related to the time after which the function repeats itself. K is related to the distance after which it repeats. Omega is related to the time after which it repeats. Okay, and you know time period is 2 pi by omega. So omega depends on the time period. Time period, you can say frequency, whatever it is, and we know time period is 2 pi by omega. That's the time after which the graph repeats or the electric field repeats. Okay, since we are discussing about electromagnetic waves, we can say it's the time after which the electric field repeats. And similarly, 2 pi by k is the distance after which the electric field repeats. Okay, let me show you the graph of an EM wave, the diagram of an EM wave, then you'll understand better. One second. Okay, are all of you able to see this animation of an electromagnetic wave propagating?
Yes, sir.
So see what is happening. You can observe that the pulses, they are traveling in the x direction, positive x direction, that too. Okay, hope you all are able to visualize that. We are looking at some section of a medium, okay, some region of a medium in which there is an electromagnetic wave propagating, and clearly the wave is propagating in the positive x direction. The pulses are moving. Tell me, what does the blue one represent? Is it the electric field or the magnetic field?
Electric field, sir.
Blue color represents electric field and the red color represents magnetic field. Now for this particular electromagnetic wave, the direction of propagation is positive x. And when electric field is in the positive y direction, magnetic field is in the positive z direction. So it satisfies the condition that direction of propagation should be along E cross B. And you look at the last point, okay, towards the end of that x-axis. At that point, they have shown you arrows which are continuously changing in length. So you observe the blue arrow. The blue arrow is going up, coming down to mean position, going down, coming back to mean position, and so on. Basically, that is what is happening with the electric field at that point. As the wave passes through that point, the electric field strength increases positively, goes to 0, decreases, again, or you can say increases negatively, comes back to 0. The field keeps changing. It keeps oscillating. And simultaneously, the magnetic field also keeps oscillating, and you can clearly see that the angle between them is 90 degrees. And the same happens at every point where the electromagnetic wave is propagating. Okay. Now you focus on that point itself, that last point where the vectors are drawn. You can see that the electric field vector is changing with time. Okay. So you can also see that the electric field vector repeats its cycle. Okay. From 0, it goes to positive extreme, 0, negative extreme, 0, and then it repeats the cycle. So there is a time period for repetition of the electric field at a particular point. Similarly, there's a time period for repetition of the magnetic field also, and their time periods are same. You can observe that also in this animation. They are oscillating in phase with each other. Right? So that's what happens with the electric and magnetic fields at a particular position as an EM wave passes through it. As long as the wave passes, the electric field, magnetic field will keep oscillating. When the wave stops passing, okay, that means when the wave disappears, the electric field and magnetic field vectors will also disappear. right? So there is a particular time period or particular amount of time after which the fields repeat themselves, repeat their pattern. That is what we call as time period of the electromagnetic wave. And omega depends on that factor. So K depends on wavelength. That's the distance after which the field pattern repeats. Omega depends on the time after which the field repeats. Just a moment. Right. So at a particular instant, if you like take a photo, literally you cannot take a photograph of an electromagnetic wave. They like, I should not say they cannot be seen. Light itself is an electromagnetic wave, but if light is going in some other direction, you can't see it. Light that enters into your eye can be seen, but light going somewhere else cannot be seen. Okay, so if you represent an electromagnetic wave at a particular instant, it looks like this. So you can see that there is a certain distance after which the pattern repeats. That is what is the wavelength. That's what they have shown also in the diagram. For example, from here to here, okay, there is one pulse. One pulse of electric field is there, one pulse of magnetic field is also there. After that, the pulses repeat. Okay, so that gap is actually 2 pi by k. That is equal to lambda. Okay. So basically, we are discussing terms in the electromagnetic wave equation, how to find out wavelength frequency. From wavelength frequency, you can tell the speed also v is equal to f lambda. And phase constant phi naught. See, I told you, this is the representation of the electromagnetic wave at a particular instant. Okay. Now, assume this is moving along the x-axis. Propagation direction is positive x. Origin could be anywhere, we don't know. Let's say origin is here. O. Now at O, exactly at O, the electric field is 0, magnetic field is 0. Fine. Assume this picture was taken or this representation is done at t equal to 0. So at t equal to 0, at the point x is equal to 0, the electric field is 0. So when you put t0 in the electric field equation, when you substitute t as 0 and you substitute x coordinate as 0, the field also should become 0. Based on that, you can tell how much is the phase constant. It will either be 0 or pi. Because sine 0 is 0 or sine pi is also 0. Okay. It can be any of them. Now, it's also possible that the origin is somewhere else. Let's say this is the representation of the wave at t equal to 0 itself, but assume this is the origin. Now, as you can see, at the origin at t equal to 0, origin means x is equal to 0. At t equal to 0, the electric field is at its positive extreme, E naught. Okay, if that is the origin and this is the wave at t equal to 0, this is the, what do you say, representation of the wave at t equal to 0. Then at origin at t equal to 0, the electric field is the strongest, positive extreme. Then you put that in the wave equation. E is equal to E naught sine kx plus or minus omega t plus phi naught. That plus or minus part also we'll discuss. So at x equal to 0, at t equal to 0, the field strength is E naught. For the field strength to become E naught, this sine function has to become plus 1. And for what angle is the sine function plus 1? Pi by 2. So the phase constant is pi by 2. So if you know the electric field at a particular position at a particular time, you can tell how much is the phase constant. Okay, you don't have to bother much about it, but if they particularly want you to find out the phase constant, this is how you do it. You can do the same with magnetic field also. If you know the magnetic field strength at a particular position at a particular time, substitute that, you can find out the phase constant. Okay, so something at one instant you should know everything about the wave, then you can tell how much is its phase constant, otherwise you can't. Okay. So let's go through the properties of electromagnetic waves. These are the properties that you need to know. First thing is that they are produced by accelerated charges. Charges at rest or charges moving with constant velocity cannot produce. But there's a, what do you say? There is an, I don't remember the word, ambiguity here. Okay, ambiguity, anomaly, I don't know what exactly to call it. But acceleration is relative, right? Displacement, velocity, acceleration, these are all relative terms. Whether an object is accelerated or not depends on the frame of reference. Okay, so this you will learn in further studies. For now, you don't have to bother about it. But what I want to say is, suppose there is a charge which appears to be accelerated as seen by one person. Then this person will say that charge is producing electromagnetic waves. But the same charge can appear to be at rest with respect to another frame of reference. Then with that frame of reference, there won't be an electromagnetic wave produced. How is that possible? If wave is produced, it is produced. How can the production of a wave depending on who is looking at the charge? Okay, that ambiguity is there. That will be cleared in further studies. For now, in +1, +2, you don't have to bother about it. Okay. So yeah, that's the first thing. They're produced by accelerated charges. Then electric magnetic field mutually perpendicular. Keep that picture of electromagnetic wave in your mind, okay, while answering problems or answering questions based on this. Either this or that moving electromagnetic wave. Okay, electric and magnetic fields are perpendicular to each other, and they are both perpendicular to the velocity or the direction of propagation. So E, V, and B are all mutually perpendicular. And in fact, velocity, that's the direction of propagation, is shown by E cross B. Next, electric and magnetic fields oscillate in phase with each other. So when one reaches the positive extreme, the other also will be at the positive extreme, strongest. When one becomes zero, the other also will become zero at the same time. Next, this is how we write the electromagnetic wave equation. You just mention the electric field equation, that's enough. From that, we can derive magnetic field. Or you write magnetic field, from that we can derive the electric field. And what is the relation between their peak values? E naught is equal to V times of B naught, where V is the speed of the EM wave in the particular medium. For vacuum, it becomes equal to C. Then speed of any wave depends on properties of the medium. So speed of electromagnetic wave depends on permittivity and permeability of that medium, epsilon and mu. Okay, dimensionally also you can check 1 by under root mu epsilon will have dimensions of speed. Okay. Fine. So I said we'll discuss about that plus minus also. Suppose the electric field, which is in the y direction, is represented like this: E naught sine kx plus omega t. And in another case, let's say the electric field is represented as E naught sine kx minus omega t. Can one of you tell me what's the difference between these two equations or these two waves?
The first equation travels along negative x direction and the second one along positive x.
Okay. If the coefficient of position and the coefficient of time, okay, are of the same sign, they could both be positive or they could both be negative also. If the coefficients of x and t, okay, position and time, have the same sign, then the wave propagates in the negative direction along that axis. Here, it's propagating along x-axis, so I should say it's propagating in the negative x direction. Fine. And if the coefficients of position and time have opposite signs, one positive, one negative, or one negative, the other one positive, okay, both should have opposite signs, then the wave is traveling in the positive direction along that respective axis. So here it will be positive x direction. Okay, now why is it so? Again, mathematics. Just a moment, I'll show you a small example. Okay, earlier we had taken the graph of y is equal to sine 2x, right? 1 second. Let's use the same graph. This is the graph of y is equal to sine 2x. Now, it's like sine kx. Okay, let's add something to this. And the coefficient of x here is positive. 2 is positive. We'll add something to this. I'll add 1. Let's say sine 2x plus 1. This is the graph of sine 2x plus 1. Now, what's the difference between these two graphs? Okay, if we put both of them in the same frame, we'll be able to understand. Anugraha, okay, you can. Just observe the graph. You look at the peak value. Actually, if I superpose both of them, it would have been better, easier to understand. But basically what is happening is this. The second graph relative to the first one is shifted to the left. Okay, for example, you look at this peak value in the first graph, it occurs here. Okay, the scale seems to be slightly different. Just a moment, let me adjust. Okay, I'll make the scale equal along the x-axis. The origin is coinciding, but other numbers are not coinciding. Okay, now it is fine. So if this axis is same, then these two are coinciding. Right. One second. Fine. The second equation is sine of 2x plus 1. Okay. This equation can be written like this. Sine of 2x plus 1 is equal to sine 2 times of x plus 0.5. So effectively, we have increased x by 0.5. Okay. If you do that, the graph will shift to the left by 0.5 units. If you add something to x, the graph shifts to the left side. You can observe that happening here. This is the peak value of the first graph. Okay, it occurred somewhere here. Whereas for the second graph, the peak is here. Okay, that same peak in the second graph is shifted to the left. So generally, when you add something to x, okay, like if the coefficient of x is positive, here the coefficient of x is 2, 2 is a positive number, and you add something to it, then the graph will shift to the left side. Okay, so if the coefficient is positive and you add something to it, it shifts to the left side. If coefficient is negative and you subtract something from it, then also it will shift to the left side. You can get those graphs from Google and check if you want. Fine. But if coefficient of x is positive and you subtract something from it, then the graph will shift forward, positive x direction. Okay. And same thing, if the coefficient is negative and you add something to it, then also you'll see it going forward. Okay. So that is how we can tell the direction of propagation of wave based on these plus minus signs, based on the coefficients of x and t. Okay. So remember, if they have the same sign coefficient, like both positive or both negative, it's going in the negative direction. If they have coefficients of opposite signs, then the wave is going in the positive direction. Okay. Fine. So we have discussed wave equation, how to find out the peak values of one from the other. Right. Try to solve this question. write the equation of electric field of an EM wave of frequency, let's say, okay, 10 megahertz. Mega is a factor of 10 power 6. Okay, you can call it million also. Mega, million are the same, 10 power 6. So that's the, let's say that's the frequency of the electromagnetic wave. The amplitude of electric field, assume, is some 20 Newton per Coulomb. It can be given as Newton per Coulomb or volt per meter also. Both are same. They are both the SI units of electric field. Frequency is given. Electric field is given. Electric field amplitude is given. And let's say it's traveling in vacuum. You know what is the speed of an EM wave in vacuum. Make use of that. Okay, ignore the phase constant. Write the electric field equation based on this. Right. You have to keep the general equation in mind. General equation is of this kind. E naught sine kx plus or minus omega t. Now, I didn't tell you which way it is propagating. So plus minus is your choice. Okay. But just fill in these values. Or let us make it more precise. Assume it is traveling in the positive x direction. Then based on that, you can decide plus minus also.
So,
How much is E naught?
sir, E naught is 20.
E naught is 20. Next. From frequency, what can you tell? Which term can be calculated?
Sir, omega.
How are they related? Okay.
Sir, 1 second, sir. I'm facing internet issue.
Okay.
Yeah, sir. Omega and F. Omega is equal to 2 pi by
2 pi by
2 pi by no. Sir, T is equal to 2 pi by omega.
correct. T is 2 pi by omega.
And F will be omega by 2 pi.
Frequency is inverse of that, omega by 2 pi. So omega you can say is 2 pi f. Okay. So omega becomes 2 pi into 10 megahertz. Mega is 10 power 6. 10 into that is 10 power 7. Okay, that's omega. Next, how do you decide plus or minus?
Sir, if both of them are in like, if both of them are positive or both of them are negative, then it's negative x direction, and then if it's
Okay.
like,
Here you are told that it's in the positive x direction. It's traveling in the positive x direction. So should you use plus or minus?
sir, minus.
Minus, correct. So that part is done. How to get K now? K depends on what?
K depends on the wavelength.
Wavelength, correct. But nothing is told to you about wavelength. Then how can you relate what is given? Or how can you make use of what is given to you and find out wavelength?
So according to the wave equation, E naught should be amplitude,
Yes.
and then so two E naught will be the wavelength.
Why will 2E not be the wavelength? Amplitude has nothing to do with wavelength.
Oh, yeah, my bad.
Is there anything which connects wavelength and frequency?
Sir, sine kx will be 2 pi by k, like the period.
Period is 2 pi by k. Okay. Huh. See, basically, in one time period, no, one pulse will get produced. So, in one time period, the wave covers a distance of one wavelength. So, you can relate wavelength and time period like that. Wavelength is the distance covered for a time of one time period. And if you know distance and time, distance covered and time taken, they'll be connected. They can be connected with the speed. It is told to you that this wave is traveling in vacuum. You know the speed of electromagnetic waves in vacuum, 3 into 10 power 8 meters per second. Speed is equal to distance divided by time. When a wave travels a distance of one wavelength, the time taken will be one time period. Okay. Let me write V itself. So V is equal to lambda by T naught, and this is what becomes F lambda. V is equal to F lambda. 1 by T naught, 1 by time period is frequency. So if you know the speed and frequency, you can tell wavelength. And from wavelength, you can tell K value. Is this clear?
Yes, sir.
Okay. So lambda can be written as V by F. V is 3 into 10 power 8 meters per second. Frequency is 10 megahertz, that is 10 power 7. So this becomes 30 meters. And if lambda is 30, how is K related to lambda? Or what's the exact relation between K and lambda? See, you said K has something to do with period of repetition, right?
Yes, sir.
K or 2 pi by K is the distance of repetition. This distance, the distance after which the EM wave repeats. So 2 pi
Yes, sir.
by K is the wavelength of the wave. Okay.
Oh, okay. Yes, sir. Yes, sir.
So lambda is 2 pi by K. Then K becomes 2 pi by lambda. You can just interchange them. And its unit will be inverse of length. Is it clear?
Yes, sir.
Okay. That way you can tell all the terms in the wave equation, and then you can write the equation itself. Okay. Next class we will discuss how much energy an EM wave carries, how much momentum it carries, how to write the expression for intensity of electromagnetic waves. Okay, that will be the end of the chapter. It's a small chapter only. Fine, we'll continue on Thursday. Yeah.
Okay, sir. Thank you.
Okay.